Good morning, everybody, and welcome to our monthly Mornings with O'Keeffe program. I'm Katrina Latka, the Curator of Education and Interpretation here at the Georgia O'Keeffe Museum. I'd like to begin by recognizing the lands of the Pueblo people on which the sites of the Georgia O'Keeffe Museum stand. We recognize and honor their elders, past and present, and celebrate the vitality of their people today and into future generations. I offer this with humility and gratitude in acknowledgement of the need to confront ongoing injustices of settler colonialism. And now for some Zoom housekeeping. If you've not already done so, please introduce yourself in the chat box. To find the chat, go to the bottom of your screen and click on chat. If you're using an iPad, the chat can be found at the top of your screen. Above where you type your message, you also have the option to send a message to everyone or just the panelists. Please also utilize the chat box for questions throughout the presentation, and our presenter, Dale Kronkright, will answer them at the end. You can also close the chat box by clicking on the X in the upper right corner. And if the chat box is in the middle of your screen, you can move it around your screen by clicking on it and holding down your mouse button and dragging it. Closed captioning is also available throughout the presentation. To turn this on, click on the CC button on your screen, which is located at the bottom or the top, just depending on your device. I would also like to extend a thank you to our members and our donors who are here today. Your support really made this event possible. If you're not yet a member and you enjoy this program, please consider joining today. Please visit gokm.org/membership to learn more. Now it's my pleasure to introduce our presenter this morning, Dale Kronkright. He's head of conservation at the Georgia O'Keeffe Museum. He recently made news here in Santa Fe and across the nation a couple of times recently. First, for his monumental undertaking of the conservation O'Keeffe's very large 1948 canvas spring. This work and accompanying materials are now on view in the Santa Fe galleries. And then again, even more recently, for securing a patent after a decade of research for what we're about to discuss today. So without further ado, Dale, why don't you tell us a little bit more about this amazing project that you've been working on to protect art here at the O'Keeffe and in the museum community at large.
Thanks, Katrina. Hi, everybody. And let's see, Katrina, can you confirm that my screen is, PowerPoint is visible?
It is not yet.
Okay, let's get that done. Here we go.
Yes, you can see it now.
Wonderful. Beautiful. So welcome, everybody. This talk is about the technology embedded in a recent patent issued to the Georgia O'Keeffe Museum to protect works of art and any vibration-sensitive payload, really, from vibration-induced damage in road and aircraft transit. Now, you can probably tell from that introduction that we're about to get a little geeky today. There may be charts, in fact, so that's early warning. Why do things in transit get damaged from vibration? Everybody has probably had an express delivery parcel crushed in transit. So we know about drops and shocks and being run over by a forklift. But what is it about vibration that could be damaging? Aren't they small little energy inputs? I've spent a career trying to understand how heritage materials deteriorate and what we can do to slow or stop that deterioration. I love physical mechanics and chemistry and optics, so I could talk about this subject all day, but I'm pitch hitting today for a speaker who suddenly had to postpone their talk, and I have no idea who my audience is out there. So I've had a couple of days to try and distill 10 years of research working with incredible engineers and scientists and try to boil that down to a simple to understand 1 hour talk. So if you're out there today, bear with me. I put this together pretty quickly. I'm going to try and explain in terms everybody can understand. what vibration is, why it damages heritage materials like works of art in transit, and what we've discovered we can do about that. So this is a video. I'm going to just stop that for a second, and I'm going to move it up. Because we don't need to see all of it. So what I want to do is I just want to differentiate for you all the difference between shock and vibration, because we're really talking about two different things. Traditional museum packing crates like the one you see here, and yes, that is a George O'Keeffe Museum packing crate for a painting, but no, there's not a painting in there. There is a facsimile painting with accelerometers attached to the canvas, to the frame, to the inner box, and so on. Traditional museum packing crates like this have been built for over 100 years to protect the artworks inside from impacts, collisions, falls, and drops. They haven't been made to dampen vibrations coming from outside sources, but they do have layers of cushions inside that are designed to compress 4 to 6 inches in the event of a major shock event, absorbing a great deal of the shock energy in a sudden rapid acceleration, or in this case, a deacceleration when it hits the ground, of relatively high displacement. For example, in this case, a 1 meter drop. So this would be the equivalent of falling off the back of a truck lift gate or falling off a loading dock in a high wind and that sort of thing. It's happened before. It's not unheard of, but in reality, art handlers, art packers, and fine art transport companies are far more careful about this than ever before. If there's a high wind and they're loading off lift gate, they'll strap the work down before they lower the lift gate. So a lot can be done to prevent this, but the question is, does your crate prevent from this kind of damage, which is what it's designed to do? But it turns out that our best crates don't offer all the protection we would like. So in this test, we're dropping at 1 meter. It lands on its sort of top edge, bounces around a little bit. The outside of the crate itself saw an acceleration, a shock of about 300 Gs, which is huge, enough to kill a human being if it happened to us. Inside, with all the packing and cushioning that we put into those things to try and prevent damage, the canvas saw between 40 and 60 Gs. Now that's a big reduction, but the fact is that catastrophic damage of a painting occurs somewhere between 20 Gs and 30 Gs. So even our best crates don't do the job we'd like them to do. So let's start the video. So you can see what a 1 meter drop looks like. So we've got accelerometers on board, wires going to a data acquisition unit. The platform is 1 meter above the ground, about 3 feet. And let's say it's on a lift gate of a truck. And a stiff breeze comes along and knocks the crate over. Ouch. So that's a shock. Everybody understands what a shock is. Now, let's take a look for a second about some characteristics of vibrations. Vibrations, unlike shock, are much smaller changes in the resting equilibrium of an object. Small forces, often randomly directed, result in oscillating changes back and forth in the acceleration and the momentum of objects in a fixed number of frequencies. That is, that they shake back and forth at only certain frequencies dependent upon the materials and structures of the object. And they often have very small amplitude displacements because the energy inputs are small. Think about some simple musical instruments that create sound by vibrating. So this is a way of sort of explaining what vibration is. A bell, which we all know, we've all rung a bell and heard it vibrate. A guitar or violin string, which most of us have been familiar with one way or another, or a drum, certainly a car door, or a trumpet. These are all things that vibrate to make an audible noise. So when something vibrates, it gets pushed or pulled from its resting position by an external force, which we call an excitation or an impulse. And if the force of the impulse is big enough, like plucking a violin string or striking a drum head, it will overcome the inertia of the object at rest and cause the object to slightly bend or deflect or move, storing some of that absorbed energy in the deflected materials of, say, the string. And then it will start to return to its rest position. And if enough energy was stored by the deflection of the internal materials, it'll move past its rest position, sort of in the opposite direction again, and then slow to a stop where it'll start going back. So that's that oscillating motion that structures take on when they're vibrating. And when they do that, they consume a little bit of the energy they're storing, like a spring, to go back and forth, because the materials, the molecules in the structures are rubbing against each other and generating a little bit of heat friction as a result of that movement. And so it slowly begins to go back, stop slow vibrating back to its rest equilibrium position. That sort of makes sense. So the important thing I want you to remember about vibration is that every bell or string or drum head vibrates at only one note. Okay, that note is defined by the size, the length, the mass, the uniformity, and the tension of that string or drum head. But it doesn't matter if the string or bell or drum head is played gently or vigorously, it still only vibrates at that one note. That's something we've all probably experienced. Doesn't matter if you hit the bell hard or barely hit it, or pluck the string hard or barely strum it. It's only that one note that will be played. So if it's displaced with a lot of force, it will obviously ring more loudly. And that's because when we hit something hard, we displace it over a bigger distance. We call that amplitude of displacement. But the note remains the same so long as the mass, the size, the tension, and the uniformity remain the same. I hope that's making sense. Went a little too far here, hang on. Takes a while for this to load. There we go. That's what I wanted to do. And it went back. Okay. Right. Can I play media? That's interesting. Okay, so these are different modes of vibrations of a rectangular membrane, which is basically what a painting is similar to. My point here is that artworks behave the same way. So for example, if the wall that the art is hanging on vibrates from the traffic passing on the street in front of the museum, generating vibrations at about, say, 5 cycles per second, what we call hertz. Or from a double bass in a jazz ensemble playing in the gallery at about 60 hertz, or a saxophone playing at 140 cycles per second to 900 cycles per second. The artwork may likewise get moved from its resting position by these vibration impulses in the air. Now, usually the force in the air in a sound wave cycling between 60 hertz and 900 hertz from a jazz ensemble doesn't contain enough force to overcome the mass of the canvas sitting still in its resting position. So the canvas is displaced very little at very low amplitude, and it rings down back to its resting state or its equilibrium position very quickly by virtue of the mass and the stiffness of the paints on the canvas. The note passes and the canvas returns to rest, and there's relatively no damage. But remember what I said about bells and guitar strings and drum heads vibrating at only one note. Canvas paintings are a great way to understand vibration because they are essentially a drum head. They are a rectangular membrane of paints sitting on top of a flexible canvas stretched over a wooden framework. Every painting vibrates at only one note. And again, that note is determined by the size of the painting, and the tension, mass, and uniformity of the paints in the canvas. When a painting is displaced by a force, the resting inertia of the canvas is changed by the amplitude of the incoming force. And if that force is small, say like the vibration from a short note on a bass at 60 hertz from that jazz quartet, the canvas will displace just a little and then slowly ring back down to the resting position in short order. But if the note of the canvas painting its resonant frequency happens to be at or near the 60 hertz that the band is playing, something very different happens called resonance. If, when tapped or vibrated, a canvas vibrates back and forth like a drumhead at 60 cycles per second, what we call 60 hertz, then as long as the bass player holds that note in the gallery of 60 hertz, the canvas will keep absorbing that energy and keep moving further and further and further in each direction at the same 60 hertz, because that's its resonant frequency note, and it'll keep moving until it reaches the physical limits of the paints to stretch and compress. Then the paint will crack where the stresses are greatest or where the elongation capacity of the paints are smallest. So what we learned is that there are two things needed to make paintings vibrate until they crack. The first thing is that the incoming vibration has to be near or at the resonant frequency or note of the painting. And the second thing is that the recurrence of those incoming vibration impulses have to last longer or come in faster than it takes for the canvas to ring back down to its resting position. In that condition, the painting keeps accelerating further and further and further as it absorbs the energy of its own note. In transit, those long-lasting vibration impulses coming in at the same resonant frequencies as the painting's natural vibration notes would need to reach a painted canvas despite the many layers of padding and protection that normally surround the painting in transit. There are frames and inner travel boxes, outer boxes, air ride truck cargo boxes, big rubber tires. So how is it that vibrations might reach a painting? An informal analysis of 125 O'Keeffe canvas paintings presented a rather alarming statistic. 71% of all paintings with recent crack propagation or extensive crack propagation, that is, cracks growing longer, becoming wider, or getting more out of plane, had accumulated totals of 17,000 road transportation miles or more. So there was at least some evidence in that survey that transit-induced vibration might be playing a role. And on average, our three-venue one-year traveling loans have about 5,000 miles of cumulative road travel and about 70 hours of cumulative vibration. So a painting of ours would easily hit a theoretical, say, 20,000 mile threshold before cracking after only 4 traveling one-year loans. So I want you to remember the Tacoma Narrows Bridge collapse if you do. Now, you obviously won't, most of us won't have been there in 1940. In November of 1940, just 4 months after it was open, the Tacoma Narrows Bridge in Washington fell apart in a wind. Here, the resonant frequency of the bridge, like the guitar string, was exactly the same as the wind vortexes, the spinning winds that were passing over the bridge. And it created resonance, just like in our painting. So this is a really wonderful or horrible example of what resonance is when the incoming impulse, in this case, the wind, is vibrating at exactly the resonant frequency of the bridge. So I'm going to speed this up. And everybody's probably seen this, but it's worth seeing. It really demonstrates what's going on. Sorry about that. So those are the new bridges. And this will be the original bridge as it's opening in July of 1940. Cars going across, the ribbon being cut, the authorities waving. And then something happened as it got windy in the straits. The wind started to pass over the bridge and curl and wrap around the bridge at exactly the same resonant frequency that the bridge had. So they tried to strengthen and reinforce the cables. That didn't work so good. And in November, this happened. That just sort of shows you the power of resonant frequency. So the next question might be, when are artworks subjected to long and continuous vibration impulses? And the answer is in transit, being moved from one museum to another for traveling exhibitions and loans. Museum artworks are moved using satellite-tracked, air-cushioned, climate-controlled fine art transport trucks and large international commercial aircraft. Traditionally, works of art are carefully packed inside custom-made, heavily reinforced, insulated wooden crates, packed within cushioned inner boxes and wrapped to seal out changes in temperature and relative humidity, so that regardless of what the conditions are outside, the inside, the painting will be kept safe and relatively comfortable. The crates are designed to resist impacts and collisions and keep out rain and snow and beating sunshine, as well as smoke, steam, and vapors in the event of, say, a traffic accident. But all the modes of transportation vibrate. When you're in your car going down the highway, you can hear your engine and your transmission. You can hear the wind on your windows. If you have snow tires in the winter, you can hear the sound that they make. Obviously, aircraft are super noisy, and we hear the engines, we hear the wind on the fuselage, we hear the air pressurizing compressor inside, and we can feel and see the wind resistance of the moving aircraft as the wings bounce up and down and twist the fuselage. Everything we hear is an oscillating vibration of pulses of air entering our ears. Humans typically hear air impulses from 20 cycles per second, or 20 hertz, to 20,000 cycles per second, known as 20 kilohertz. The air oscillations are generally driven by some solid, like a bell, a window, a fuselage, an engine, or a tire, vibrating at those same frequencies and pulsing the air and all the structures around it. In 2011, at the close of a 3-city European tour of some 70 George O'Keeffe paintings, I got them back to the studio and noticed that in some of the paintings, the cracks had propagated. That is to say that, again, they've become visible for the first time, or they lifted out of plane, or they grew longer, or they grew wider. So on the screen, you can see George O'Keeffe's painting, White Bird of Paradise from 1939, which is just spectacularly beautiful. And we're going to be on the right looking at a transmitted infrared photograph of this area sort of right in the middle. And what's beautiful about transmitted infrared photography is that if there's a crack in a structure or a crack in the paint layers, the infrared behind the painting, transmitting through the painting, goes through the cracks easier and faster and in larger quantities than it would go through solid paint and canvas. So what you see here are the cracks in the paint that we saw after that 2010-2011 travel. And so we do infrared photography of paintings that are at risk before and after travel so that we can determine whether cracks have propagated and gotten wider. If they've gotten wider, we'll be able to see them as these bright lines and changes in plane in a transmitted infrared photograph. I also use transmitted infrared photography to determine whether my consolidation techniques in trying to close up the cracks are successful. So we do it before and after treatment, and we do it before and after travel. So I warned you that there might be charts. I'm just sort of fulfilling my promise here. In engineering, we look at how much power is being transmitted by a vibration source, like a truck in this case, or a commercial jet airliner, by looking at how the vibration energy is being transmitted at each frequency from about 3 cycles per second, which is sort of similar to the movement of an earthquake, through the frequencies of moving vehicles and aircrafts, which are up to about 500 cycles per second, like a car engine. Looking at the power distribution curves, which is what these are, or charts, looks sort of intimidating, but it can be easily understood. These are the power spectral distribution curves, or PSDs, of commercial transport trucks in the three main vectors of vibration directions. So vertical accelerations or vertical vibrations is when the truck is moving up and down. Longitudinal vibrations are movements in the direction of travel or front to back in the truck. And lateral accelerations are accelerations that are moving side to side. All vibrations are almost always a combination of these three, but looking at all three of them over the same period of time tells us how the vehicle is responding and where the power and the vibration is coming from. So it's important to see all three. The red line in each graph is the US military standard for maximum vibrations allowed in each direction across the range of vibration frequencies. So this red line that you see up here in each of the graphs, whoops, didn't mean to go to the airplane graph quite yet, is the military standard. The blue line is an average of many experimental transit that we made in a fine art air ride transport truck moving at highway speeds. And I'll describe what the yellow lines are in a second. But the important thing to understand here is that the higher the peaks, the higher the power that's being transmitted to the object inside the truck bed. And then these are, the bottom scale is a logarithmic scale of the vibration frequencies. So what you've got here is about 3 hertz. You have 10 hertz here. This is 50 hertz. So the first line is 10 hertz. The second line is 50 hertz. This is 100 hertz. And then we go up to 200, 300, 400, and 500 hertz. And what this tells us is that at about 6 hertz in all 3 directions, there is a peak that's pretty sizable at about 6 cycles per second. Again, that's sort of earthquake type motion. And this is the rocking response of the truck as it hits a large current of crosswind or air. And what's interesting to note is that paintings really don't respond to these very low vibrations because they're moving with the crate and with the truck as a sort of a rigid solid. In this case, there's no stresses on the canvas at that area. But then when we get to about 15 hertz, we notice that we have some fairly large accelerations in the vertical and up and down direction, small ones in the longitudinal direction. And that kind of makes sense because big trucks don't accelerate very quickly and they don't slow down very quickly. And we also have some fairly large peaks side to side happening in that area right there. And then things after about 50 hertz begin to really fall off. The energy that's being transmitted in these frequencies is fairly low. Most of the energy being transferred into the cargo box of the truck is in this range of 10 to 50 hertz. And you can see in the side-to-side direction down here at the top that, in fact, our average trial runs at highway speeds exceeded the military standard for side-to-side vibrations. And that's because when we were making the tests, we were being hit by some fairly substantial crosswinds. The important thing here is that trucks and aircraft transmit a tremendous amount of energy between these 2 yellow lines. The bulk of the energy coming from highway travel comes in this range between about 20 hertz and about 50 hertz. So let's say between 10 and 50 hertz, the majority of the energy coming from a truck is being transmitted at those notes, those frequencies. This is the same kind of curve for an aircraft. And then this is a heat map of vibration in a commercial aircraft. So you can see if this is vibration, the pilots have got a nice smooth ride up front. Things are vibrating a little bit. Right above the wings is getting a lot of vibration. You can see the landing gear on either side here and how those hatches vibrate quite a bit. The rest of the cargo hold kind of smooths out very nicely. That's good news for cargo, kind of bad news for passengers. But the important thing here is that these two lines are our 10 to 50 hertz range. And then we notice that in this range from 50 hertz up to about 600 hertz, there is a whole lot of energy being transmitted by commercial aircraft in flight. So even though this is a scatter point graph, the portion between 10 and 50 hertz is almost exactly the same amplitudes that are being experienced by trucks. In some cases a little bit less, but generally speaking, just as high as what trucks experience, with the added input of these higher frequency energy inputs between 50 and 600 hertz. So we use measurement devices called laser Doppler vibrometers, manufactured by Polytech Incorporated, a German company, to measure the resonant vibrations in works of art, the inner travel boxes that the painting is resting in, and the outer crates. A laser Doppler vibrometer uses low energy infrared laser with a constant frequency of light, and inside the vibrometer instrument, there is an interferometer mirror that splits the beam into two, one focused on the surface to be measured, in this case, the surface of a painting, and the other sent internally to a photodetector as a reference. Both beams end up going to a photodetector and compared. In simple terms, the frequency of the light that returns off a vibrating object goes up as the surface vibrates towards the vibrometer, and the frequency similarly goes down as the surface vibrates away from the vibrometer. That's how it makes the measurement. This is the Doppler effect that you've probably experienced listening to the sound of an aircraft as it approaches and then flies away from you. As the airplane approaches you from a distance, the sound or note of its engines that you can hear are compressed by the velocity of the plane as it's approaching your ears. The sound frequency goes up as the sound waves get more compressed and the frequency gets higher. As the plane moves away from you, the engines are vibrating at the same note, but now the sound waves are being stretched out by the velocity of the plane moving away from you. So the frequency of the sound goes down. The vibrometer measures the difference of vibrating frequencies of the object and the original steady state frequency of the reference laser, and then calculates and displays how far the surface is moving when it vibrates, the displacement amplitude, the note or the frequency at which the surface is vibrating, the velocity of the vibrating surface as it passes through its normal resting position, measuring the rate of ring down until it gets back to its resting equilibrium position, and it measures the maximum accelerations that the surface experiences as it moves from its point of greatest displacement and then accelerates back to the resting point. It's a truly amazing instrument. So this is called a multi-point vibrometer, and each of these is a vibrometer with the laser and the interferometer, and they're all focused at different points on the painting, which we vibrate slightly with the tap of what's called a modal hammer that measures the input vibration. And this is some of the data that you get in real time. So the blue line in this graph is the easel. The blue dot down here is the easel. You can see the easel moving back and forth. And then this is the painting with its collection points. And you can see the painting actually moving, middle of the painting moving back like this, sides of the painting sort of racking. So it helps us understand exactly how a particular painting responds to vibration inputs, the frequency or note that it plays when it's vibrated, and how it's moving. It actually can tell us where there are active cracks in the painting, where the paint is not fully adhered to the canvas below, and helps us in that diagnostic way as well. This is an image of George O'Keeffe's painting, Series 1 from the Plains, 1919. It's an oil on canvas measuring 27.5 by 23.5 inches. It's secured within its traditional shock cushioned custom wood crate. With me is Dr. Vikrant Palan, team lead and business development manager for Polytech, and Dr. Aaron Vonderleith, application engineering manager at Polytech. They're both vibration engineers and they are totally cool. The painting is mounted inside its traditional inner travel box, cushioned at the corners, and then secured and anchored inside its custom fabricated outer wood and foam crate. We've secured the painting so that we can vibrate it with the crate cover off, using a shaking device that's programmed to sweep through the vibrations that the crate would normally see inside a fine art transport truck being randomly vibrated. So this is the outer crate with the cover off. This is the inner travel box with cushions at the corners holding the frame. So that's the setup that you're going to be seeing. So this is the data visualization that we see once we've collected all the data. So the outside rectangle that you see is measuring the movement of the outer crate. The inside rectangle that you see is measuring the vibration of the inner travel box. And then the gridded points that you see here are the canvas painting itself. We're vibrating the crate from the back, in this back corner, and we're vibrating in a way so that it combines both up and down, longitudinal, and lateral vibrations in all three directions. And this is the kind of data we get. The chart here at the bottom is the magnitude of the canvas displacement, how much the canvas at that little point right there, which is circled, how much the canvas is actually displacing or moving front to back. So that's the magnitude of the displacement per unit of input force. And then the bottom scale is the vibration frequency, right? So there's 20 hertz right there. There's 40 hertz right there. This goes all the way out to about 100 hertz. So this is the vibration frequency profile of the canvas painting. And we're looking at the measurement. So over here are some numbers. We are looking at how the canvas moves where the marker is at 23.5 hertz. It's moving a little over 20 microns per Newton of input force, and it's moving like this. So in this case, when the canvas turns red, it's moving towards us, and when the canvas turns blue, it's moving away from us. And this is called a 1-0 double drum mode. So in other words, the middle of the canvas right here is staying almost motionless, but the vibrations have been split into two, and the vibration to the left and right of the midpoint are alternating vibrating in a double drum mode. Now, what's important to point out here is that notice how red and blue the canvas is as it's being vibrated at 23.5 hertz. This is the resonant frequency or note of this canvas painting. But notice that the outer box and the inner box are never turning completely red and never turning completely dark blue. So they're not moving as much as the canvas is moving. So now we're going to look at some of that actual data, and I'm going to switch my screen here and share a slightly different screen, and then we'll come back to this. Go here, and okay. I'm not sure that worked. Scans, great. There we go. Okay, so this is the actual data visualization. Instead of being just a GIF or a video of it, this is the actual data visualization of exactly what we're looking at: the outer crate movement, the inner travel box movement, and the painting movement itself with our vibration source, the shaker pot down here. And we're going to start the animation. My marker is down here. So what you're looking at, slowed way, way down, is the behavior of the outer crate, the inner crate, and the canvas at this peak down here at about, we can see what frequency we're looking at about 7.5 hertz. And what we're looking at is kind of the motion of the outer crate. So when we shake the crate top vibrates a great deal. Notice that the inner travel box is moving in lockstep with the outer crate, as is the painting. They're all moving as if they're a rigid body at these low frequencies. Now I'm going to move this cursor and we're going to move through the frequencies and just watch how the behavior of the canvas changes. So right now we're at about 10 hertz. And again, things are moving pretty much the way they were at 6. We're going to go up here to about 12 hertz. We're at 11.8. And there's our first single drum mode. That is the middle of the canvas painting is moving forward and back. And it's moving at about this displacement, about 3 microns per Newton of incoming force. We're not sharing it. We don't have to shake it very hard. We don't have to have the same amplitudes of vibration to understand what the behavior of the painting will be, because we know the input force and we can extrapolate out from the small force what the painting displacements would be at a high force. So notice now that the outer crate is kind of rocking back and forth. So this corner is turning blue and then it's turning red. Notice that the inner box is moving a little bit less than that, almost in unison with the outer crate, but that at 12 hertz, there's a resonance here. And now that we're above 10 hertz, the canvas is starting to see stresses occur between moving areas and unmoving areas. That's where the stress takes place. Let's continue to move up. So we can move, say, to about 14 hertz, which is right here. And at 14 hertz, we can see that, again, the outer crate is really rocking at the top and the inner crate's doing the same. But notice that the canvas is no longer vibrating back and forth at its single drum mode. In fact, it's almost moving exactly like a rigid solid with the outer crate and the inner travel box. And again, it's moving in a rigid solid because 14 hertz is not the note of this painting, okay? But as we move closer and closer to that 23.6 hertz, you can see the canvas behavior starting to change. And we'll get right here at 23.6. And now the canvas is developing that double drum mode that we saw before. The magnitude is about 20 microns per Newton of incoming force. And what's really interesting, as we pointed out before, is that the outer crate is not moving very much and the inner crate is not moving very much. They're slightly out of phase. They're kind of moving, not quite in opposite directions, but they're not moving together. And the canvas has hit its fundamental frequency, its resonant frequency. This is the note that this canvas rings at the most. Notice that right after that, as we move off it, the ringing begins to stop and the canvas begins to more behave increasingly like that rigid solid till we get to this little peak right here. The displacement is not very high. It's 2.5 microns per Newton of incoming force, but we can see the 2-1 double drum mode. So instead of the double drum vibration being side to side, the double drum mode is now occurring top to bottom. And we'll finish moving through here to the next sort of displacements. We're starting to see here a triple drum mode side to side. So this is a 3-1 drum mode. And there's that 3-1 drum mode sort of fully developed right there at about 43 hertz. So what's interesting is that all these vibration impulses are coming from a truck continuously at the same time. And the canvas is moving in all of these directions, depending on which vibration frequencies happen to be coming in the most. But what we do know is the highest canvas displacement and the highest stresses being placed on the paint, which is the restraining layer of this whole system, is right here at 23.6. Okay, so let's go quickly back to our presentation. Okay, so This is a diagram of what happens as fatigue begins to take its toll with these little tiny vibrations over a long period of time. This is a cross-section diagram of a painting. These are the warp and weft threads of the linen canvas. The gray represents the ground layer, the primer layer that's put on, and of course the blue are the paint layers. And it acts essentially as a continuous glassy film. But as the painting begins to vibrate and bend, essentially what happens is it undergoes tension as it moves away from the backing. The paints get pulled apart and they become thinner. And then in the opposite direction, the paints become compressed. Eventually what happens, usually at the thinnest areas, at the high points of the threads, you will see cracks begin to occur in the priming layer because the priming layer is the stiffest. And that forms a little bit of a hinge. And then the vibrations focus all of their movement at these hinges. And these hinges move back and forth, and these areas, they get pulled further and further apart until ultimately we have very large hinges that have broken through all the layers, even cracking the threads below. Now we have a series of isolated tension and compression going on, making cracks worse and worse and worse. So cracks in paintings are forever. They never go away. They can be occasionally laid back down, but they will come back because there just is no way to recreate exactly the same structure that we had originally when the artist laid the paint onto the surface. So here's our vibration in the double drum mode again at 23.6 hertz. But what I want to point out here is this graph. So what we're looking at here is the vibration of the outer crate. This is about 19 hertz. That's the natural note of the outer crate itself. The next curve is the vibration of the inner travel box. And notice, because the inner travel box is contained and held in place by the outer crate, it almost has the exact same natural frequency. But what is interesting is that the amount that the inner box is moving is higher. The red line is higher than the blue line. That means the inner box is not moving less because of these wonderful cushions that it has at the bottom. In fact, the inner box is moving more than the outer box. So why would the inner box with all these cushions vibrate more with greater displacement than the outer crate itself, which is sitting right on the truck bed? Now, if we look at the frame of the painting, which is the next line, the frame of the painting is held rigidly to the inner box, and it's basically moving pretty much the way the inner box is moving. But then let's next look at the curve of the canvas, which we've seen before, and you can see how much the canvas is moving at its natural frequency. This is the effect of having vibration inputs from trucks and airplanes come close to the resonant frequency of the plane or the truck. And what we're noting here is that the pads that we're using to protect the painting in a drop or a collision, in other words, from a shock, are actually amplifying the vibrations, not diminishing the vibrations. And what's happening is the pads are going in phase. They're moving together at the same rate in response to the vibration inputs. After measuring many paintings in the George O'Keeffe collection of all sizes, some cracked, some uncracked, some lined, some unlined, some with heavy paints, some with light paints, what we found is that all of our paintings vibrate. They all have a note, but that note vibrates within a range. And that range is about 10 to 50 hertz. They all vibrate within this range. And that just happens to coincide exactly with the range that trucks and aircraft, even fine art air ride trucks, vibrate the most. So in reality, from a vibration standpoint, our paintings would be safer if they were just strapped to the front of the truck. Of course, there's all kinds of reasons we can't do that, but we're not doing, with our wonderful shock absorbing crates, we're not doing the work any favors from a vibration standpoint. Every minute and every second, that the object is in the truck and the truck is moving on the road, it's vibrating. So what to do about it? Once we discovered all these problems, I had an idea. And the idea was that if we could rigidly attach artwork to an inner platform, inner transit gantry securely, and then we could isolate that inner gantry, that inner suspension framework from the outer box, then we and tune that inner system so that that inner gantry only vibrated below the danger range of the painting. Let's say I could design an inner framework, an inner gantry that would vibrate only at 6 hertz, well below the damage zone of our paintings. Then the paintings would never see anything close to their resonant frequency, and their vibration would be diminished. And the fact is that every painting has a vibration lifetime. It can only vibrate so many times over so much time before a crack begins to appear. We can't know exactly what that vibration lifetime is, but what we do know is if we can cut the amount of vibration at the painting's natural frequency in half, that one act alone will double the travel life of every painting in our collection. So that became the design criteria, is trying to isolate an inner gantry, an inner support system, and prove that we could make that vibrate at a low frequency of about 6 hertz and protect everything on board, all the artwork attached to that inner frequency, from receiving anything despite what might occur in the outer crate. So this is the Polytech Testing Center in Michigan. We're vibrating the crate. We're subjecting it to various kinds of laser Doppler vibrometers so that we can understand the motion. And the patent reflects a number of all the different isolating types of devices we have tried. We've tried active electronic isolating devices to see how effective they might be. They're kind of like noise canceling headphones. They measure the input vibration. They create an equal and opposite vibration, thereby isolating the inner gantry system, the art holding system. But the problem is that takes a whole lot of power and a whole lot of batteries, and we are simply not comfortable putting large lithium-ion batteries inside a crate with a bunch of works of art. The other problem with active vibration damping, of course, is that if it happens to break down on one of the isolators, you've got nothing protecting your artwork from vibration. It's not a redundant system. It has a single point of failure. And museums, when we're transporting irreplaceable artworks, love redundant systems. So if there's a break in the outer wall of the outer crate, there's an inner wall that will protect it. If an isolator that's protecting from vibration happens to go out, there's another one backing up that one. And we wanted to have isolators to protect from vibration as well as from that 1 meter drop. So these were tremendous engineering problems to have to overcome. We've gone through about 6 iterations of those design problems, going through isolators that don't work, going through isolators that do work, coming up with ways to create redundant isolating systems, changing the art mounting corners and art mounting systems about 6 different times, creating a better and better and more rigid inner gantry system that would hold that. And so that's what the patent reflects. And that is sort of where we are at this point. We're now working on the last iteration, which has modeled perfectly, in fact, the inner art enclosing system vibrates only at 6 hertz, regardless of what's going on outside. We've engineered the corners and the outer framework and re-engineered that so that it will withstand that 1 meter drop. So the characteristics that we wanted to achieve in the patent are getting better and better. And at that point, Katrina, I think I'll stop here and entertain questions.
Dale, thank you so much. We definitely geeked out. It was wonderful, though. There's definitely several comments in the chat talking about how wonderful it was to do exactly that. And we do have a few questions, though. And hopefully I'm reading them properly because they are sufficiently geeked out as well. So let me start with one who asked kind of early on, is there a difference in the vibration propagation between oils and watercolors? Don't know if you tested that out.
Yeah, absolutely. Right. I mean, so you can imagine that just like a bell, a thicker bell rings at a lower frequency, a thin bell rings at a higher frequency, restrained object like a canvas painting rings one way, an unrestrained thing like a watercolor vibrates at a different thing. So it's absolutely true. The key thing we have tried to do in the patent and in the design is that paintings, canvas paintings, have the lowest frequency range of almost all the artwork. So if you can protect a canvas painting, you can protect almost anything else using the same design criteria. So that's how we attacked it. We attacked the problem by trying to address the hardest thing to isolate.
Makes sense. And I guess kind of building on that, is there, all right, I'm going to read it out loud. Is the frequency of the fundamental primarily a function of the size of the canvas? So AKA a larger painting, lower fundamental.
Great question, and certainly that's what we were expecting, but we got surprised. We learned a lot about the way paintings age, and I want to point out that there has been a lot of painting mechanics research that has been done before me. There were studies in the 1980s, studies in the 1990s, and we sort of reinforced those observations, and that is that very shortly after the execution of a canvas painting, normally canvas painting has a nice stretched taut canvas and paints are applied to that, and the canvas is doing all the work of holding the load. But just a few years, literally, after the initial stretching of the canvas and the application of the paint, the whole system changes. The canvas threads begin to stretch and slip past each other and become more and more relaxed. And very quickly it becomes the painting on the surface, the actual design layers that we're trying to preserve, that are doing all the work of supporting and restraining movement. So it changes. It's almost the opposite. It's not the canvas that's restricting movement, it's the paints that are restricting movement and taking up all the stresses of being stretched and compressed back and forth. So what we found, what determines the resonant frequencies of a painting are how thick and how stiff and the size of the paint. So it's a combination of size and thickness and types of paint rather than, say, the weave of the canvas in older paintings. That's the thing we didn't expect. We thought the canvas would be the #1 contributing factor to resonant frequency, and it's really not. It's size and the condition of the paint. So a cracked painting vibrates at a much higher frequency because it has more movement. A painting a lower frequency. A painting that has a continuous paint layer is stiffer and vibrates at a higher frequency. So we can determine whether cracks are active or passive.
That's a fascinating discovery. So much of the longevity of the art is up to the decisions of the artist in the end. Yeah. So does framing with glass versus without glass make any difference?
It does. Putting a sealed backing on a painting or putting sealed glazing and closing an airspace between the canvas front and a piece of glazing. In our case, we use optically coated acrylic so it won't break. Creates an airspace either behind or in front of the painting. It's called an air piston. And that air piston has the effect of damping the movement of the canvas and slightly raising the frequency. So you can lower the movement, even though the canvas is still going to vibrate at its resonant frequency, it's not going to move as far. So that's why you'll notice when George O'Keeffe Museum travels its paintings, we have both a sealed backing behind the painting and we have a separate sealed airspace in front of the painting. And that helps us mitigate vibration damage by keeping the canvas from moving too far. We don't have to actually touch the canvas with anything. Just the sealed air volume will do that work for us.
I know we're just slightly over time. I wonder if we could hang in there for a couple more questions real quick.
Yeah, sure, anybody. And for those of you that can't, thanks so much.
We have an interesting question here. One person says, all very old paintings, for example, Renaissance masters, are quite cracked. It seems so natural, us, viewing them in the gallery, and we see these cracks all the time. So are we going to create an unnaturally uncracked set of O'Keeffe's for future generations?
Well, I think that ultimately when O'Keeffe's paintings become as old as Renaissance master paintings, they'll likely have all the cracks or a similar pattern of cracking that the masters Renaissance paintings have. But hopefully it'll take a lot longer to get to that point. I mean, ultimately we are talking about a rigid glassy material that's being vibrated and moved all the time. And this is a fatigue reaction. In other words, cracks don't happen instantly. We're stretching molecules all the time over a long period of time, many, many years, until ultimately some of those molecules break apart, right? And then that puts an extra load on the immediately adjacent molecules. They break, that puts a load on those immediately adjacent molecules. And then the potential, that hinge effect of moving around those broken molecules increases the loads and then ultimately develops the crack, right? So it does take time. This is fatigue reaction. But what we know is that vibrating a painting at its resonant frequency accelerates that process. So if we can transit paintings below their resonant frequencies, we can slow that process way down. And that, in effect, is what we're doing. We're slowing the rate of deterioration. So maybe, for example, it'll, instead of taking, 520 years to crack a painting to that degree, it might take 1,000 years to crack a painting to that degree, because we've cut the rate of deterioration in half. We know that O'Keeffe didn't like cracks in her paintings. She worked very hard with her conservators to repair cracks as soon as they appeared. So really, we're trying to reflect her aesthetic for her own work by preventing this damage.
Great, and a two-parter to end us. Are the paintings packed only one per box? And is the O'Keeffe yet shipping our works in these containers?
That's a great question. I wish we were shipping our paints in these containers. But we have made improvements on all the factors that are included in the patent that was just issued, and we've filed additional patents to reflect our new technologies. So while we're in the process of building our technologies, once you release something into the public, then kind of the cat's out of the bag and everybody can copy it. So we want to wait until the patents have been issued, until we start traveling our paintings in our own boxes. So right now we're using my very best wooden crate with foam cushions that we know don't work. And we are putting backings and glazings on the front of the painting to try and mitigate that damage, but we are racing as fast as we can to try and get them into our crates.
That other part of the question was, in these crates, can you fit more than one work in them?
Yeah, right. So traditionally, wooden crates with cushions don't have more than one in them. Museums have started to do that more and more. Our crate, yes, you can use the entire inner support container that vibrates only at 6 Hertz. It'll load from both sides, both front and back. It is packed and unpacked standing up. You don't have to lie it down to pack and unpack it. And it will hold multiple paintings on both sides. So the net effect is that you can get more paintings into this inner gantry and travel them safely than you could perhaps with a traditional wooden crate. And that lowers the carbon footprint of the whole system. The crate's made to be reusable over and over. And all the parts in the crate are designed to be recyclable. So in that sense, we're trying to get the carbon footprint as absolutely low as we can get it in a reasonable transport system.
So cool. I wish we could have gotten to more questions. People have such amazing thoughts. And Dale, thank you so much for all your time and putting together this presentation so quickly. You know, I think there's so much more to come from this project and your discoveries on this. So thank you so much.
You're welcome, Katrina.
All right. Thank you all for joining us.
Bye-bye, everybody.